Hello everyone. In the previous lecture, I discussed about the two nuclear integral techniques, namely RBS and ERDA, which are based on a charged particle beam bombarding the target, and we are measuring either the backscattered particle like in RBS or the forward emitted recoils in ERDA. Now I will discuss two techniques which are based on the measurement of the gamma rays that are emitted when a projectile reacts with the target. So they are called nuclear reaction analysis, NRA, and particle induced gamma emission, PE. In fact, in particle induced gamma emission, mostly we use proton as a projectile, and so it can also be called as proton induced gamma emission. But there are other PE reactions where the deuterium beam also can be used, or even other beams can be used, alpha can be used, and so on. Okay, so first let me discuss the NRA, nuclear reactions. So there is a distinction between what NRA techniques I am discussing. It basically they are based on the resonance in the nuclear reaction cross section. So those techniques which are based on the resonances in the nuclear reaction cross sections we will call NRA. And other techniques, so NRA and PG, basically you have nuclear reactions, emission of gamma ray, but those techniques where there is an enhancement in the cross section at particular energy of projectile, that means there is a resonance, we are clubbing as NRA, as historically it has been used as NRA. So resonant nuclear reaction means at a particular energy of the projectile, there is a significant enhancement in the cross section for the reaction. The two most commonly used nuclear reactions are projectile is nitrogen 15. You take note of it. Projectile is fluorine 19. Normally, no proton will be used as a projectile, but here nitrogen 15 or fluorine 19 is the projectile, and we want to study hydrogen in the material. So hydrogen is a target. So nitrogen 15 plus proton, carbon 12 plus helium, and plus a gamma ray is emitted. Now the gamma ray is 4.43 MeV, and the ER means the resonance energy. This is resonance energy, energy of nitrogen 15 at which resonance occurs. So I will elaborate this using this graph. What we have here is the cross section versus the energy of the projectile nitrogen 15, and corresponding energy of proton also is used. Suppose you want to detect nitrogen 15 using proton beam, that also you can do, but applications are more with regard to hydrogen determination using nitrogen 15. So what I am showing here, that the cross section is going here, and then there is a, see, this is log scale. So here the cross section is 100, 200, and here it is 2 lakh. So 200 to 2 lakh, 200,000. So there is a 3 orders of magnitude increase in the cross section. 1,000 times the cross section is rising. So there is one more resonance at, so this is at 6.405 MeV of nitrogen 15. This is at 13.38 MeV of nitrogen 15, and there are more resonances, but we focus on the first resonance, 6.405 MeV. So that means what? If you bombard a material containing hydrogen at the surface, and at 6.405 MeV of nitrogen 15, you will get a very high increase in the gamma ray yield. And so the moment the energy of nitrogen agrees with the resonance energy, then there will be threefold increase in the gamma ray yield, 3 orders of increase in the gamma ray. Another reaction is fluorine 19 plus proton or hydrogen, oxygen 16 plus alpha, and the gamma ray of 6 MeV is emitted. And this happens again at 2 energies, 6 MeV and 15.3. Again, we use the 6 MeV gamma energy of the fluorine 19. So essentially you are making the resonance. So if the energy of the projectile is matching with the resonance energy, there will be significant enhancement in the gamma ray yield. So how do you get the information? Yield at the resonance energy. Gamma ray yield at resonance energy gives you the concentration of the hydrogen. So when you are starting with the resonance energy 6.4 MeV for nitrogen 15, resonance condition. This resonance condition is met at the surface. So you are probing the surface hydrogen. Then you increase the energy of nitrogen 15 in steps of 0.1, 10 keV and so on. So you are gradually increasing the energy of projectile. The resonance condition is met in the depth of the. So you understand this point. If we suppose this is the target, and you start with the first 6.4 MeV, you will see the hydrogen here. If you want to see the hydrogen here, you have to have higher energy, maybe 6.5, 6.6 or so, because the projectile will lose energy in this. So as if you want to probe hydrogen at different depths, you require to have higher and higher projectile energy. And you can calculate from the energy at which resonance is achieved, you can calculate what is the depth of that position. So that is the yield at higher energy gives you the bulk hydrogen. So that means at higher energy you are in the bulk. Resonance condition is made in the bulk. And what is the depth? E minus ER. So E minus ER upon d by dx will give you dx. So if you know the resonance, the resonance energy, the energy of projectile at which the resonance occurs is divided by d by dx is known. You can find out the depth at which the hydrogen was probed. So this is the principle of resonant nuclear reaction or NRA. So how do you get the depth profiling? As I already discussed, you measure the gamma ray yield as a function of nitrogen 15 beam energy, projectile beam energy. So you can see here the nitrogen 15 beam energy is increasing from 6.4, or you can go slightly low, 6.3 or so. Let's go 6.35. So you can see here each point, here the point will be 6.5, 6.6, so 100 keV. You can go even lower, smaller steps. And so the experiment involves bombardment of the target. In fact, I forgot to tell you about the experimental arrangement here. That this projectile beam is passing in a vacuum, and one can divide the target depending upon. You have a target that like a rotating wheel, circular wheel, and you have the targets at different. So we can have 4, 6 targets at a time. One of the target will come in the beam path, and when you bombard simultaneously, you will measure the gamma energy and intensity. Energy is known, intensity with the sodium iodide thallium. So you don't need to have a high energy, high HPG because you are not interested in the energy measurement. So you can have multiple targets and measure the gamma ray intensity using sodium iodide thallium detector. And so you can see this spectrum. This 6.4 MeV yield of hydrogen corresponds to surface, because that is the resonance condition, the initial beam energy. And as you increase the beam energy, you are probing the bulk hydrogen. So this target, actually they have implanted hydrogen in the sample at a particular energy, and then you get probing whether this is like a demonstration of depth profiling of hydrogen in a material. Okay, so the yield, the gamma ray yield depends upon some factor, which is depends upon the cross section and detection efficiency, the stopping power, and the how many counts you get per microcoulomb that gives you the hydrogen concentration. So counts versus energy gives you concentration versus depth, as I mentioned just now, and depth profile gives coming from the E minus ER, energy of the incident energy minus resonance energy upon stopping power d by dx. For this carbon, this nitrogen 15 bombardment of hydrogen, the resonance, whatever resonance we saw in the previous slide, resonance width was only 8 keV. And that width determines the depth resolution, because that gamma ray yield If you vary by less than 8 kV, it will not make a difference. So when you vary by 20 kV, 30 kV, you will see the hydrogen at different depths. So up to 10 kV, you will see it is only same hydrogen you are probing by varying by 8 to 10 kV. So the steps of natural beam energy will be 20, 30 kV and so on. So this width of the resonance gives you the depth resolution, 8 kV WHM upon the stopping power of nitrogen 15 in that matrix, and that happens to be 46 nanometer in silicon. The stopping power of nitrogen 15 in silicon can be obtained is known, and 8 upon that stopping power gives you the depth resolution. So you can imagine at nanometer scale you can probe the hydrogen. So you will find there are not many techniques whereby you can probe hydrogen. Then normally, you will see that you can like hot vacuum extraction and quadrupole mass spectrometry for low jet for hydrogen isotopes. You evolve the hydrogen by heating it, and then you evaluate them by mass spectrometry. But if you can do it non-destructively, nothing like that. So NRA is a unique technique to probe hydrogen, because hydrogen is invisible in many other non-destructive techniques. What are the other also like neutron activation analysis? You cannot do NAA of hydrogen by NAA. By RBS, other forward scattering spectrometry, you cannot do, because this is sensitive to heavier jet only. Then X-ray and OZ electron based spectral X-ray fluorescence. Hydrogen X-ray very, very small, So most analytical nuclear analytical techniques, hydrogen is invisible, and therefore NRA, in fact, the growth of NRA technique was basically because of its potential to determine hydrogen in materials. And also you will find technologically there are many materials which they may have, hydrogen may have dramatic effects on their physical, chemical, electrical properties. And so it is important to know if there is a hydrogen impurity into this material. Particularly, in nuclear technology, the hydrogen diffusion in zircon. You are using water as a coolant. Hydrogen is generated, it may diffuse into the zirconium, and zirconium hydride may lead to stress corrosion cracking. Similarly, the steel is prone to embrittlement by hydrogen, and so many technologically important materials, hydrogen induced embrittlement or corrosion is a big problem. And so if you have a non-destructive technique, this will be the best to determine hydrogen and its depth profiling in these materials. So mostly NRA is used for hydrogen depth profiling in technologically important materials. Okay, so I'll just give you a couple of examples of hydrogen determination in technologically important materials. One of the examples was, the glass. The borosilicate glass is used for vitrification of high-level waste. This high-level waste is a waste material in nuclear technology. Now it is not called a waste because it contains a lot of important radioisotopes which are useful. So when you irradiate uranium in the reactor to produce electricity, and you get plutonium also, and many fission products are produced, you want to recycle the uranium and plutonium in the subsequent reactors. And therefore, what you do is you separate uranium plutonium from this spent nuclear fuel, and that the raffinate of that reprocessing, you can condense to make what is called as the high-level radioactive waste. This high-level waste is a big problem to know how to manage it. So what they do, they vitrify, immobilize in a glass matrix, and that glass matrix should retain this radioactive isotopes for a time period of hundreds of thousands of years, because it shouldn't come out. And therefore, the chemical durability, the leach rate of the glass is determined as a function of radiation doses. People are studying radiation damage. And so the glass can be attacked by water. And therefore, how the leach rate will depend upon suppose you dip the glass in water, then there could be leaching of sodium. Sodium is in the glass. The sodium borosilicate glass. So sodium is taken as a marker for leach rate determination. So when you put a glass in the water, sodium will come out in the solution, and hydrogen will get into the glass. So that study was done. What is the mechanism of leaching of sodium from glass into the water? And you can see here depth of by this reaction. So nitrogen 15 beam energy is increased. So they have directly put in terms of the depth in microns. So 0.1 to 1 micron thick, 1 micron thick glass sample. And the depth profile of hydrogen is here. And depth profile of sodium is here. So for sodium, sodium 23 P gamma, magnesium 24 was used, which is giving you 1.32 MeV gamma ray. So you can do sodium depth profile. It also has got resonance at a particular energy of proton. So what they see that from the surface, sodium is coming out. Depth means this is the surface. So from the bulk, sodium is coming out into the water, and hydrogen is getting into the bulk from the surface. So surface is in touch with the water, high hydrogen, and gradually water is ingressing into the. So you can find out the rate at which the exchange is taking place. And another important thing that water H plus is not coming as H plus, but H3O plus, hydrated hydrogen. From the ratio of the signal due to hydrogen and sodium in the NRA spectrum, you can find out what is the form in which hydrogen is getting into the glass. So this was a very important study. Way back in 1979, it was studied, and it in fact led to the understanding the mechanism of interdiffusion between the alkali metal ion in the glass and hydrogen in the water. Another study was the hydrogen adsorption by palladium nanoparticles. This paper was published in Angwate Chemie. You can imagine the kind of studies people are doing, because the kind of information that you get from these techniques are unique. It is not a routine analysis, but it is a very important technique, very useful information you get from. So let me try to explain this. What is happening? The palladium nanoparticles are used as a catalyst for hydrogenation of alkenes. Okay, so they wanted to study whether it is the hydrogen is getting adsorbed on the surface of nanoparticles, or the volume, there will be some hydrogen in the bulk of the nanoparticles. So what is the role of surface adsorbed hydrogen and volume absorbed hydrogen? So what they found, that by this technique, NRA, one could distinguish between the surface adsorbed hydrogen and volume absorbed hydrogen. And you can see here the depth profiles at a different function of the hydrogen pressure. They studied 10 to minus 7 millibar to 2 minus 5 millibar, and the surface adsorbed hydrogen and the volume bulk hydrogen could be distinguished. You can deconvolute this depth profile of hydrogen, and then as a function of the hydrogen pressure, they found that the surface adsorbed hydrogen plays a role only at low pressure. High pressure, the bulk hydrogen also starts playing its role. So I will not go into the details. The point I wanted to emphasize was that you can study the role of surface and bulk hydrogen in understanding the particular chemical reaction that are taking place. This is the kind of study people are doing. Now I will come to the another technique of nuclear reaction analysis called the particle-induced gamma emission, where some of our colleagues have done a lot of work in this area. So PE at Bhava Atom Research Center, we have an accelerator called FOTIA, Folded Tandem Ion Accelerator. It is a 6 million volt terminal tandem accelerator, and so you can have 6 into 2, 12. If we have 6 million volt terminal, then you can have 6 plus 1. 1 plus 1 into 6, 12 MeV proton beam. But normally you get 5 MeV, 6 MeV proton beam, and you can have higher beams also, carbon, oxygen, and so on. So this is the photograph of the setup. We have a scattering chamber here, 50 centimeter scattering chamber, and for particle-induced gamma ray, you have a HPG detector at 90 degree, and you have the ladder, target ladder. You can bring different targets in the position of the beam by raising and lowering this target holder. And chamber is at vacuum, because you may require to have, suppose you are doing RBS, you are determining the charged particles. So there are different nuclear reactions with low Z elements induced by mostly protons, but there can be reactions by deuteron, like sodium D deuterons can be done. And so what is important is that you should have a suitable gamma ray in the range 100 to 1000 keV or so. So for low Z materials, you will find lithium, boron, fluorine, sodium, magnesium, aluminum, silicon, phosphorus, sulfur. All of them have suitable nuclear reactions with their isotopes, and the gamma energy are also well resolved. So if you irradiate a sample with the proton beam of the order of 2 MeV and detect the gamma ray emitted by these reactions using a germanium detector, you can do the determination of concentration of the elements present in a target material. So mostly this nuclear, see, once you go to higher target isotopes, like let us say you want to do for iron, cobalt, nickel, or so, what happens? First of all, you have to cross the Coulomb barrier, you have to have higher energy. Once you have the high energy for proton beam, then the compound nucleus will be formed with a excitation energy, high energy, and so it will evaporate neutrons. So you will not have one reaction. You will have multiple reactions, Pn, P2n, P3n, and also you may have P alpha and so on with lighter ones. And so for higher mass nuclei, the gamma spectra will be very complicated. Whereas for low mass nuclei, there are only simple, these are like inelastic scattering or low lying states are involved in the nuclear reaction. So the gamma ray spectra are not very complex. So PG is a very simple technique. You are not going to for depth profiling because you are using protons. So the stopping power is not very high. You have a very low, so resolution is not good. As I mentioned in the RBS also, that experiment for 4 MeV proton beam, that resolution was 1 micron. So normally, you would look for a nanometer scale depth resolution to do depth profile. So this is one of the experiments we did at Kotia, quality assurance of nuclear materials. So as I mentioned, these are not meant for routine analysis. You just want to determine concentrations and then so. So this is a specific application that certain rods they contain boron and certain rods they do not contain. So you want to qualify them whether there's no mixing. So you want to know whether this rod contains boron or not. And so you use the nuclear reaction, boron 10, P alpha, lithium 7, and there is a 429 keV gamma ray is emitted, and that is measured using this germanium detector. And the target is very long, so you cannot keep it inside the chamber because chamber height is only 1 to 2 feet. So what you do, you take out the proton beam in air by isolating the vacuum with a tantalum foil, and proton beam is a proton will not lose much energy in air. So you can put this big sample at the surface and then determine the gamma ray that are emitted in the nuclear reaction. So you can see here the 429 keV for the sample which contain boron, and without boron you don't see a peak. So this is a kind of experiment where you do quality assurance, means you want to ensure the people who have the manufacturer of the rods want to assure the user that this does not contain boron or this contains boron. So you have to provide a certificate of QA that this is meeting the requirement. So that is the kind of experiment people do in the using proton induced gamma emission. This is another important work for PG of glasses used for vitrification of high level waste. So again, let me try to give you some background to this study. As I was discussing in the previous one also, that borosilicate glass is used to vitrify the high level waste. The high level waste is generated during the reprocessing of the spent nuclear fuel, and there will be different types of fuels. And one of the fuels now for the future is thorium, thorium-based fuels, and that will contain THO2. Now, when you dissolve thorium is very, so particularly sintered thoria, no, very difficult to dissolve. And so, to dissolve thoria, there may be use of hydrofluoric acid, HF. HF is very reactive acid. And so, when you do reprocessing, ultimately, some fluorine may get into the glass matrix when you are immobilizing you are supposed to remove fluorine, but suppose some fluorine is left, then this fluorine in the glass matrix may lead to appearance of crystalline phases, some fluorides, calcium chloride, or some, it may precipitate out, because some like rare fluoride may precipitate out. And so you want to know what is the tolerance of fluorine in your glass. Even glass, the fluoride can affect the chemical durability of the glass, because it may start enhance the leach rate. And so for the long-term performance of that, this glass will retain the fission products and actinides. It is important to again ensure that whatever content of fluorine is there in the glass, it is a safe limit. It is within the tolerance limit. Therefore, every time dissolution of glass is where you can determine fluorine by ion selective electrodes. That is very simple. But then you have to dissolve the glass and do the study. So that is a very tedious. And suppose you have multiple samples. Here is a very simple technique. You take the glass as it is, non-destructively, just bombard with the proton beam for a few seconds, few minutes, and the gamma spectrum tells you what is the fluorine content. So again, the same reactions I have shown for the constituents of the glass. You can have sodium borosilicate, it will have sodium, aluminum, silicon, boron. There may be some extent of alumina also. And if there is a fluorine, then you will get this 110 keV gamma ray. So in the one shot, all the constituent of the glass will give you the gamma spectrum 110. Again, there is one more reaction of fluorine with the proton, PP gamma. You have 197 keV, sodium 440 keV. There is a 511 keV gamma ray also. So by 2.4 MeV proton beam, you can determine the concentration of not only the constituent of the glass like silicon, aluminum, sodium, boron. You can also determine the fluorine content and thereby qualify that the fluorine content. So there is a threshold of 1%. You cannot have more than 1% fluorine in the glass. You can quickly do the experiments and find out what is the content of fluorine in this glass matrix. So I just give you some of the examples of NRA and PG. Due to lack of time, I could not give more examples, but the point I wanted to emphasize was that these nuclear analytical techniques are not meant for routine analysis. They are meant for a very specific application in high technology areas. And so one has to, it is not the only technique you will be using. There can be a combination of other techniques, and to understand the process, to understand whatever the mechanism, also to qualify the high technology material. So there are many other examples, but I do not have time to describe. But I hope I'm able to bring the point that ion beams, the charged low energy ion beams, can be used in characterization of materials which are being used in many applications. So that's all I have to say. Thank you very much.